the shape of the universe is a topic of intense debate in physical cosmology, with its local and global geometry being primary areas of focus. The curvature of the universe provides insight into its spatial structure and is described by general relativity. However, the topology of the universe remains an open problem as it cannot be determined from its curvature. Cosmologists differentiate between the observable and entire universes and debate whether the universe is finite or infinite. Understanding the potential topological and geometric properties of the universe is crucial in this discussion. The universe's shape can be modeled mathematically as a three-manifold corresponding to the spatial section of the spacetime of the universe, with the Friedmann-Lemaitre-Robertson-Walker (FLRW) model being the most commonly used, while observational data suggests that the universe is infinite and flat. Other possible shapes, such as the Poincaré dodecahedral space, the multiply-connected three-torus, and the Sokolov-Starobinsky space, cannot be ruled out. The theme of this passage is the structure and geometry of the universe. The author discusses two aspects: the local geometry, which is concerned with the curvature of the observable universe, and the global geometry, which examines the topology of the entire universe. The observable universe can be likened to a sphere extending outwards from any observation point for 46.5 billion light-years. While it is possible to look back all the way to the Big Bang, the farthest we can see is the cosmic microwave background. Due to its opacity, the observable universe may either encompass the entire universe or be smaller than it, and experimental investigations show that it is very close to being isotropic and homogeneous. It is therefore conceivable that the structure of the entire universe may be determined through observation. However, if the observable universe is smaller than the entire universe, scientists may not be able to determine its global geometry through measurement. The author also discusses the different mathematical models of the global geometry of the entire universe, which are consistent with current observational data. To test the accuracy of a mathematical model, scientists look for novel implications that must exist if the model is correct, and devise experiments to test those phenomena. Finally, the author describes the curvature of any locally isotropic space, which falls into one of three cases. Non-Euclidean geometry deals with curved geometries, which can have either positive or negative curvature. A positively curved space, like a sphere, has angles in a drawn triangle that add up to more than 180 degrees. In contrast, a negatively curved space, like a saddle shape, has angles that add up to less than 180 degrees. The density parameter, symbolized by omega, determines the curvature of spacetime. Omega 1 indicates negative curvature, while omega of approximately 1 suggests nearly flat curvature. Two methods can determine omega: calculating the average density of all mass energy in the universe and geometrically measuring an angle across the observable universe. While astronomical measurements indicate a spatial curvature close to zero, local geometries of spacetime generated by relativity demonstrate that 3 space can be approximated by the familiar Euclidean geometry. The global structure of the universe encompasses the geometry and topology of the observable universe and beyond. A constant curvature geometry is limited by the local geometry, and any topological defects create significant analytical complications. Investigating the global structure includes determining whether the universe's geometry is positively, negatively, or flatly curved, and whether its topology is simply a multiply connected. The dimensionality of space is another area of investigation, with physicists proposing an explanation for why we observe 3 dimensions. The boundedness of the universe is an open question. It could be infinite or finite, with a well-defined volume in the latter scenario. If the universe is finite, it may or may not have an edge, which creates complications in mathematical and conceptual treatments. Closed manifolds, like the 3-sphere and 3-torus, have no edges and are considered to be compact without boundary, making them suitable for calculus applications. The fluctuations of the cosmic microwave background, CMB, reveal something intriguing about the properties of our universe. There seems to be a missing power on scales larger than the universe's size, suggesting that our universe is finite and multiply connected. Recent research indicates that the CMB spectrum fits best with a gigantic 3-torus cosmos where all 3 dimensions are connected. The curvature of the universe also influences its topology. A spherical universe with positive curvature has compact topology, while flat or hyperbolic spatial geometries can be either compact or infinite. Commonly, it is thought that a flat universe means an infinite one, but a flat and simply connected universe is finite. The Planck mission's final results indicate a positive curvature for our universe, meaning its extent could be infinite or part of a finite structure such as a 3 torus or Klein bottle without dark energy. A flat universe would expand forever at a decelerating rate. In a universe with positive curvature, elliptic geometry describes it, and it can be thought of as a 3-dimensional hypersphere. Ultimately, our universe's fate may be similar to that of an open universe. Poincare dodecahedral space is a positively curved space that resembles the shape of a football and is one of many 3 manifolds that could describe our universe. The concept of an open or closed universe in cosmology typically refers to whether the curvature is negative or positive. However, this definition causes confusion with the mathematical definitions of open and closed used in topology. In math, a closed universe is a compact manifold without boundary, while an open universe can be either a closed or open manifold. For instance, the FLRW model assumes a boundaryless universe, where a compact universe could be considered a closed manifold. Though the Milne model can be used to model an infinite universe within a sphere, observations rule out a negative spatial curvature. Nonetheless, the model is useful as a background for gravitational fields due to diffeomorphism invariance.